my talk will be divided in two parts. So it's really two talks in one, okay? So two parts. So first part is joint work with Pierre Roussillon. So it will really be about shapes and really related to what Irene just presented before. And second part is really about implementation and coding of this KeOps library that Jean just advertised a few minutes ago, and it's a joint work with Benjamin Charlier and Jean Feydy. Okay, so first part. My main research area is shape analysis and what is called computational anatomy. So there are two different applications, two distinct ways of thinking about deformations in shape analysis. First one is to speak about registration. So registration is very important application in image analysis, and particularly in medical image analysis. So you may need to register images, okay, from different patients for medical images of any organ, or you may need to register shapes that you have segmented from the images. So here are just a bunch of different applications that I've worked on. But sorry, I was saying the first goal is the registration. Okay, so you want to be able to match one shape to the other in order to, for example, co-register many different images to one template. And the second goal is more ambitious, is through deformations you can try to study, to perform statistical analysis of deformations. And okay, so for example, Stéphanie Alassonère talk yesterday spoke a little bit about this problem, and so, for example, here are applications that I've worked on with different people, and you have here brain analysis applications, where here you have hippocampus shapes, so you have many of these shapes, and you manage to co-register them to get a unique template shape. Here's the same with the whole brain, but you are guided with location of sulcus lines. And okay, so this is work with Guillaume Ozias and during his PhD. This is work also with the same team at Pelletier-Salpêtrière, which is now called Aramis. This is a joint work with people in Australia about audio processing problems. So they want to study the shape of the ear. Okay, so this is just to explain a little bit the motivation. So now I have a few slides about the deformation model that Irene already explained a little bit, but I need to go through again because it really is the basis of the registrations algorithms that I've worked with, although it's not really necessary for the main topic, but I need to go a little bit through this. So this is work, the LDDMM framework. So LDDMM means large deformation diffeomorphic metric mapping, and it's just a general framework to build deformations from integration of velocity field. So you have a flow equation like this, and you control the velocity fields, and you build deformations that are ensured to be diffeomorphic through these flows. And the mathematical construction ensures that you can define, if you do it properly, you define a Hilbert space over the space of velocity fields, and the norms, the integration of the norm of the velocity field of these velocity fields give you a cost of deformation. Okay, and so here is just an example of a kind of deformation that we can get with these tools. And in a registration framework, when you do in exact matching, it meaning that you want to register one shape to another through a deformation, but you will not manage to do it exactly because you have noise, and for many reasons you don't want to do exact matching. So you have, as usual, a variational problem where you have a penalty, so this deformation cost for the regularity, and a data fidelity term that will measure the dissimilarity between the two shapes. So the matched shape, I mean the deformation of the source and the target. And so, as Irene explained, that they are the main focus of all these tools about currents, varifolds, and that I will present now, normal cycles, is about modeling this data fidelity term. Whereas here, in these few slides, I'm speaking about the LDDMM model. So the first part, okay? So so my main point here is just to explain that in the LDDMM framework, when you look at the discretized version of the theory, you end up with equations that involve the kernel K of the Hilbert space V, of the Hilbert space of velocity fields. And so you get this type of equations with convolutions of the kernel, okay? And here the QIT are just the discretized points of your shapes, okay? To say it very quickly, okay? But so the main thing here to notice is just this appearance of this kernel and the fact that we compute this type of convolutions. And also very important is the type of kernel that we use, and this is Gaussian kernel, this is a Cauchy kernel, and this type of kernels are the most used in applications, and they model all the framework, okay? Once you've chosen the kernel, you've chosen everything from the model. And you see this sigma v parameter, which is a scale parameter, which really tells you how you will at what scale you will look at the deformation. Okay, anyway, so there are now geodesic equations. So again, I'm going very quickly, but so I cannot explain, but you can write a Hamiltonian formulation of the optimal path that you get from your discretized version of the framework. So okay, once you have discretized the shapes, you have points along the shapes, and these finite number of points, they obey at the optimum, at optimalities, they obey some geodesic equations, and that can be written in Hamiltonian formulation using P, Q, momentum, position parameters. And okay, so this is just, I cannot go really through this, but I have to put this here I had to put this here because I will come back to it later. Okay, so now I'm speaking really about the other side, so the data attachment term, so the data fidelity metric that you want to model for the shapes. And as Irene explained already, you have this currents model that was proposed a long time ago now, and during my PhD. And so I have to also go through it because although Irene explained, but it's really the basis of the next model, the normal cycle. So I have to go through it again. So the first idea of this current model is to model the shapes. So now we're speaking about shapes as just curves or surfaces. You can model such objects, in any case, any oriented submanifold, as a current. So a current is something that integrates over, that act on differential forms. So once you have a surface S, for example, you can consider its integral over, the integral of any differential form over the surface, which writes like this. And this move your representation of surface into a vector space. The vector space was currents. And so for any shape, you can associate the current like this. Okay, and so the very nice thing about this model is that once you've done that, you can use functional analysis tools to build norms, so functional norms on currents. So since currents are dual objects, the norms that we consider are dual norms. And these dual norms can be expressed again through the kernels, okay? Because everything that we do here is just about Hilbert spaces, okay? So all the tools that we use are, all the functional spaces that we introduce are Hilbert spaces, and so they have kernels, reproducing kernels. And so again, you have this type of equations where when you want to measure the norm, the square norm of the current associated to a surface, you do a double integral of the kernel of the space W over the surface. And what you have here are the tangent spaces at each location along the surface. So integrate this information like this. So again, I'm going very quickly. I'm not explaining the current representation, but just to show a case where it works well. So here is an application with the audio application that I was speaking about just before. And for this type of shapes, the ears, which have a very quite complex geometry, but actually they are quite look alike between people, so it works very well, okay? But there are some problems with currents, and it comes from the fact that we need to, it's an orientation, I mean, curves and surfaces, when you model them as currents, have an orientation, they need to be oriented, and this causes this type of problems, where here, for example, you have a spike in one shape that you want to register to another one. No, actually, the one, yeah, the first shape is a circle, and the target is an ellipse with a spike. And when you compute a registration between the two, what happens is that this spike is disregarded by the metric. So what you end up is this type of deformation. And this type of problem is even worse because here you don't have any spike in the shapes, but you create spikes because actually these spikes are not counted in the metric again. So they appear freely in the deformation process. Of course, it depends on the scales. Okay, so you have a scale parameter for the deformation, sigma v, that I was speaking about just before, and another scale parameter for the current norm. And depending on the way you fix these parameters, you will not get into these problems, but of course, it stays a problem. So, okay, so of course, what is missing here is all these varifold frameworks that Irene was presenting just before, which is an answer to this type of problems. Okay, so with varifolds, with the non-oriented version of varifolds, you don't have any notion of orientation of the shapes, so you will not get this type of problems in the registrations because you don't have this effect. But now, to introduce the normal cycles, so what I need to say is that the main motivation for normal cycles is first to solve this problem of orientation, and second, to take into account the curvature and not only the tangential information in the shapes. Okay, so what is normal cycles? It's a second order model which will take into account curvature information. So First, okay, to introduce normal cycles. Normal cycles is something that exists in geometric measure theory. It was developed first by, I mean, the real notion of normal cycles is dates from the 80s, but it's really based on the works by Federer in around these dates. So with all the works about positive ridge sets and curvature measures. And so the main, the starting point is this formula, the tube formula, which is, you may know that when you take a set V and you enlarge it, you take the volume of the enlarged set, volume of V epsilon. So it writes as a polynomial in epsilon, and the coefficients of the polynomial are exactly the curvatures, the generalized curvature of the set, I mean actually of the boundary set. So first constant term is the volume, then the area in case of surfaces, then here is the mean curvature, here is the Gauss curvature, okay, and this is quite nice. And it is the basis of the theory of normal cycles because, as I will explain just after, yeah, okay. So you have this bijection between any position x and any normal vector to the surface, the boundary surface of the set. And so if you associate to xn, x plus epsilon n, you end up at a position along this, along the boundary of the enlarged set, and you get, I mean, and through this bijection, you can build this theory about normal cycles that I will explain. Okay, so I need to give some definitions. So, and I need to look at the. How much time do we have?
Yeah, half an hour.
Half an hour?
Sorry, no, 15 minutes. Sorry.
15 minutes, okay. Thank you. Okay, so a few definitions about normal cycles. So first, when you, as I just explained just before, so you have the epsilon tube around any compact subset is just what I explained before, okay? The enlarged set, you take all points that are at distance lower than epsilon of any set. Okay, and now you can define also normal vectors in a very generalized sense by using this notion of normal vector, which is that which is used, I mean, it's very usual in convex analysis, okay, where you say that a vector is normal if when you take the scalar product with, okay, so you take U, a vector, and you take X is your basis vector, and you take any other Y vector. So let's say the set is convex, then if you take X minus square scalar product with U, if this is lower or equal to 0, then you say that U is a normal vector. So this is very known in convex analysis, and if you take a kind of limit when epsilon goes to 0 of this notion, you get the notion of normal cone, a generalized notion of normal vector. Okay, and so what does it give for usual sets? So if you look at, for example, a closed curve here in 2D or 3D, you get as normal vectors at most points the usual ones, okay? This is normal vector in this direction, this one is the other direction. But at the endpoints, you get a bunch of normal vectors, all these half cycle here, and half spheres here and here. And this is very important because, in fact, the fact that we consider all this type of normal vectors will be very important in the model. Okay, so now the unit normal bundle is just the set of all normal vectors attached, unit normal vectors, in this sense, attached to any point on the curve of surface that you consider. Okay, and so what is very, very nice with this theory is that when you consider this unit normal bundle, actually it forms a submanifold, a closed submanifold of dimension d-1 in the space which is considered, but in fact the space considered is in fact Rd cross Sd-1, okay? So if I come back to this example, so all these points in red here belong to R2 cross S1 here, R3 cross S2 here, and in general it will be Rd cross Sd-1. And the unit normal bundle NC is a closed submanifold of dimension d-1 in Rd cross Sd-1, okay? And since it's a closed submanifold, you can define an interior and an exterior in a canonical way. And so you can consider an orientation of this submanifold, and you can say, okay, let's take the current of this submanifold, okay? And this is the normal cycle. So the normal cycle is, again, it's a current, but it's not a current associated directly to the shape itself. It's a current associated with the normal bundle, the unit normal bundle of the shape. Okay, so having said that, all the rest is just standard stuff, or almost standard stuff. But first, the link with curvature measures. So I was speaking about curvature measures and this tube formula before. So why this model of normal cycles encodes curvature? Because if I come back to this formula with a polynomial, with a tube formula, okay, actually you can localize it. So here C is my shape and B is any Borel subset of Rd. And so if I take the tube around this set, it's again expressed as a polynomial in terms of the epsilon. And the coefficients here are actually curvature measures. So they correspond to integral of the curvature measures restricted to the Borel subset, okay? And so this is standard, and now if, okay, yeah, so this is what I was just saying, sorry. Integral of the curvature measures over the subset B, and now they can be expressed through action of the normal cycle. So the normal cycle is a current, so it acts on differential forms. And if you let act your normal cycle to a canonical differential form, which is called Lipschitz-Killing canonical form, which is completely fixed, okay, this does not depend on the shape, then you recover exactly these curvature measures. So for any curvature, for example, if you think about a surface, so you have some canonical form that when you let the normal cycle act on it, it will give you the integral of the mean curvature. You have another canonical form that when you let it act on, let the normal cycle act on it, you will get the Gaussian curvature, the area, and the etc. in general case for any dimension. Okay, and this correspond actually, you can decompose the space of differential forms. So this is not the space of differential form, but this is space of d-1 vectors, which is the basis for the differential forms. And you can decompose this space into a direct sum of spaces, which are just very easy to define. And these canonical forms, the Lipschitz-Killing forms, they take values in these fk. And so each fk corresponds to a particular kind of curvature measure, okay? So I need to be careful with the time. So now all this, I had no time to explain, but all this theory, at the beginning, it works with positive rich sets, okay? Which means that for any point along the curve, you need to have a unique projection of the enlarged of the tube on the shape, okay? But you can enlarge the theory by considering unions of sets of positive reach, so UPR. And of course, this is needed in our model because we want to be able to model shapes that are discrete shapes, such as unions of segments or unions of triangles, in this case of meshes. I will skip this, sorry, because I have no time. Now, just one slide about the model for the actual model for computing a norm on the space of normal cycles. So again, we work with kernels because we want to put, as I explained before, with currents, a dual norm on the space of currents, but here on normal cycles. So we define kernels. And since now we have a current in the space RD cross SD minus 1, we have a product space. So what we can do is to define a product of two kernels. So one will be for the RD part, one for the SD minus 1 part. And you do it a usual kernel, like a Gaussian kernel for the space part here. And you can use Sobolev kernel metrics, for example, or simpler kernels for the spherical part, okay? But anyway, in the end, what you get is this type of formula where you, again, take double integrals over the normal cycle with a first kernel on the special part, a second kernel. Okay, so this is for, sorry. I'm very sorry. Kxy is all this product of two kernels, sorry. And here are the tangent element at x and y, but x and y here are, as it is explained here, the points in RD cross SD minus 1, not just the usual points, okay? So this is just the formulas that I proved that we had before for the currents, but now it's in the enlarged space RD cross SD minus 1. Okay, so this here is just to explain that when it comes to discretization, you can decompose all your shapes. So in case of curves or surfaces, you have discretization via segments or triangles, and you can decompose the normal cycle into different parts, and each part corresponds to a specific FK space that I was explaining before, meaning that you will evaluate separately the norm on these parts, spherical, planar, cylindrical, and they will evaluate different types of curvature. So a few examples of registrations with normal cycles, and just to explain that in some cases, very complicated cases like these shapes here, these curves, you get better results with normal cycles. So what is important to understand with normal cycles is that they model the curvature, and more specifically, they will put large weights on the branching points like this, here and here, and also the boundary points of the curves. And this is why in the registration process they are well matched, as you can see here. These are 3D curves actually, okay? And just two examples with surfaces where you show a difference between varifolds and normal cycles for registration of surfaces. So here is a result with varifolds. So maybe Yes, okay. So you have two, these are actually retina surfaces, and what you have to, where you have to look at is here and here at the corners. You see that with varifolds you have, well, it's not a big problem, but you have small problems with the corners, okay? Whereas when you register with normal cycles, you really solve this type of problems. Okay, so if I do it again here, if you look at the corner points, they are really well registered. And this is because they are points of high curvature. Another example with hypopotamus shapes, where also you get better results with normal cycles. But maybe I will not comment because I want to skip to the second part. So I have 5 minutes.
Yeah, a little bit more because I started.
Yeah, I started late, I think. Okay, so second part is really different. So I'm sorry now. I will completely move from. I mean, it's of course it's linked, but I will move from math. So since 2 years ago, we started to work with Benjamin Charlier and Jean Feydy to enhance some codes that we had for computing convolutions of kernels, because as you saw in my previous slides, it's really at the center of this type of algorithms. So we realized that we could do more with this type of algorithms and be very general to propose something that is perform computations which are very general, as I will explain. So first, motivations, and this is linked with the previous part. As you saw in my slides before, you have, for example, these equations, which are the Hamiltonian equations for the geodesics in the LDDM framework. They involve gradients, taking gradients of the Hamiltonian, and the Hamiltonian is expressed through a convolution of a kernel K. So you take gradients with respect to the two variables, momentum and positions. And this gives you the ODE system that you will need to solve in order to get the forward model for your deformation. So in order to build a deformation, you need to solve this type of equations. And once you've done that, when you want to optimize through a given, with a given variational problem, you need to take the gradient because you want to do some gradient descent style optimization. And so you need to take second order differentiation. And so for this type of application and for many other applications, you need to get, I mean, you don't need, but it's really helpful to have automatic differentiation, okay? Otherwise, you get up with very complicated codes. And so in neural networks toolbox, now you get very easy to use automatic differentiation tools, so like PyTorch, for example. And so we decided that we could base our algorithm, and we could use this toolbox to code the algorithms. And second motivation is this type of computation that is also expresses here. I express convolution through a Gaussian kernel. This type of convolutions appears everywhere in the computations of LDDMM. And this type of flow also, for example, this is, if you put a weight here, it becomes, no, actually, this corresponds to the computations that you get when you compute varifolds metrics, okay, with some given kernel. And so this type of computations, which are just convolutions via these functions, are really needed everywhere in the codes, and we want to have fast computations of this type of sums. So In the library that we propose, what we decided to do is to be much more general and to propose computations of any of these types. Okay, so here so think about the sum of the Gaussian kernel, but here you replace the sum by any reduction. So by any reduction, I mean not any, but there are several ones that we implemented. So for example, of course, the sum, but we can take the mean of a bunch of anything, okay? Instead of a sum, you can take the argmean. K-mean, arg-k-mean, what it means that instead of computing just the minimal term, you want to take the K minimal values, okay, or the K argmean indices, and also different types of reductions that I will speak about just after, log sum XM and softmax, which are very useful, for example, for optimal transport applications. And so this is the type of reductions that we will deal with, and the type of function is any type of functions that depend on, again, the basis, the model of the operation is just this Gaussian convolution, but now you replace this formula exponential by any type of formula, so f is any function. You have some variables that depend on I, variables that depend on j, and parameters, if you want. And so f is any type of function like this. And so what we want to do is to first to compute this reduction by staying linear in memory, meaning that we don't want to store all the coefficients ij of these functions, which would be the case if you would use, for example, just for this operation, you would directly compute the matrix of this exponential and then do a matrix vector product, but we don't want to do that because you want to stay linear in memory. And also, as a bonus, and also maybe parallelize on GPU because we want to be fast, we want to parallelize these operations. And as a bonus, we can get automatic differentiation, as I will explain. So I have a few slides of really implementation stuff. So first one is about the GPU architecture of the NVIDIA CUDA devices. Okay, so you don't need to look really at all these details, but just to note that there are four types, I would say, of memory when you use a GPU device. So first, host is just the usual RAM of your computer, okay, the host. So this is outside of the GPU card. You have the host memory. Now you have, and this is large, okay, several gigabytes. And you have also a global memory for the GPU, which is also several gigabytes. So it's large memory. So when you do an application using GPU, most of the time you need to transfer as a first step data from the host to the device. So we transfer data from here to here. And then you get to more involved types of memory when it comes to parallelized computations. So the two other kinds of memories are very small. So I may not be very accurate here when saying it's a few kilobytes here, actually, but anyway. So there are two types of localized memory when it comes to do computations at the thread level, meaning that each thread here is a particular small processor that will perform computations in parallel, okay? So for these threads in the GPU card, you have two types of memory. So local memory, which is attached to each thread. So directly, the thread can store its own local memory. And also a shared memory, which is a small concept, a bit different. Shared memory is also very local, but it's shared between different threads inside a common block of computation. I will explain a bit more just after. Okay, so I'm really sorry, it's really about implementation and no more mathematics. But so again, another slide to explain how we do the reduction. So when we have a reduction like a sum of Gaussians, for example, we want to do it parallelized on a device, and we end up with two different schemes of computations. So when you look at these diagrams, you think about each color being a thread, so being a small processor computing the reduction, for example, a sum. So starting from the first index to the end. And you can, let's say here you have nine threads, okay, so it's not a great GPU card, but just to explain. And so the very direct parallelization is to say each thread will compute its own own reduction for the corresponding I index. Okay, so here along this axis you have the I index, so the output of your computations, and along this axis you have the J index for the sum. So you perform the computations from 1 to n, okay, directly like this. But when it comes to implementing it, because of this particular thing of the shared memory specification, when you want to implement it on a GPU card, you need to take care of this shared memory because it's very small memory in terms of size. And so what you can do is to separate your computations into different blocks. I mean, this is standard for GPU coding. And so each block will process on the same block of data for the Y, the J index data. Okay? So what happens here in this algorithm is that each thread loads its corresponding, so it's written, where is it written? It's written here, actually. So each thread will load its own yj variable into the shared memory, and this yj variable will be accessed by all the threads within the block. Okay? So, anyway. So you have this type of scheme that will parallelize your computation, or you have a 2D scheme which is very similar in fact, but the difference is that each thread will take care only of a small part of the computations. So you divide your computation into blocks, into 2D blocks instead of 1D block. And each thread will compute only a part of the sum or part of the mean reduction. And at the end, with this scheme, you need an additional step to reduce further. Okay, so if you have computed the sum for this block, you need to sum them at the end. And so it looks like this is better than this, but in fact, in some cases, this is better because you may, when you use this type of scheme, every thread is blocked. I mean, okay, it's very complicated. It's not obvious to explain, but in some cases this is better. Anyway, so now I go to automatic differentiation, and then I will just show you a few examples, and it will be done. No examples? Okay.
We're already like 18 minutes.
Yes, you're right. Okay. Sorry. So just one slide about automatic differentiations. How is it is done in the code? So again, it's really about implementation. So in the code, what we write is formulas, like, for example, exponential of a scalar product of two vectors. And internally in the C++ code, it is expanded as a template classes. Okay, so exponential is a class templated with scalar product of x, y. So these symbols really means the template of C++, if you know about this, but otherwise never mind. And what is nice with this coding is that you can derive the gradient of the formulas directly using template evaluations. So everything is, this is just to explain that all the chain rule differentiation is done at compile time, okay? So once you write a formula, it is a class for the C++ code, and you take the gradient, it is also, it expands directly at compilation as a new class, which gives you the formula for the gradient. Okay, so maybe I would skip, I don't know, I will skip the log sum up reduction, which is a nice, there is a nice trick to compute log sum x per reductions, but anyway. So one slide to say that you need to, if you are interested in this type of computations, you can look at the website, okay? And okay, you can note also that we have a package to install it directly, pip install PyTorch, and this is so we have good performances, but I will skip this because I want just to show you. I'm sorry, just 2 slides more, and that's all. Just 2 examples, actually a bit more, but 2 examples here on this slide. So we realized that we could use this type of, I mean, you could use KeOps to do a very general algorithms. So for example, you have here k-means algorithm, and we believe that we have very, very, very good performances for this type of algorithms. For example, you have 5,000 classes, how much is it? Yeah. The dimension is 60, and this is 500,000. Yeah, thank you. Number of points, and this is done. The one iteration of k-means is done in this time. Okay, tenths of second, and this is a k-nearest neighbor classifier. Also very, very good performances. So we think that we are very good, but we need to check. And other types of applications for Gaussian mixture or fitting. This is Jean, one example by Jean, actually. Radial basis functional interpolation, so we can invert kernels through conjugate gradient solvers. And also applications to shape analysis, of course. So, of course, LDDMMM registration, which is much slower, but that's a problem of LDDMM, but it works perfectly. And optimal transport, regularized optimal transport, which is fast, very fast. And so also you can look at Jean neutral box, but he already advertised. Okay, so thank you for the
attention.
Okay,